Hello, in this video we are solving example to determine v of t or I of t for t greater than 0 in a transient analysis. First we'll see what are the steps to determine v of t or I of t for t greater than 0. Steps are same for all transient analysis type of examples. First step is draw the equivalent network at t is equal to 0 minus. Then second step, draw the equivalent network at t is equal to 0 plus. Last step is draw the equivalent network at t greater than 0. Now, if you check the previous videos, within that we have solved example to find the initial conditions. And if you observe that, you will find the same step. Only change in this determine v of t or I of t for t greater than 0 examples is whenever you will find the integer differential equation, in case of find the initial conditions, you are putting t is equal to 0 plus to find the initial condition. Here, whenever you will get integer differential equation, you will get that equation by applying KVL or KCL for the equivalent network at t greater than 0. Whenever you will get that integer differential equation, when we want to determine v of t and I of t, what we will do? We will solve these examples. We are not putting t is equal to 0 plus, which we did for the initial condition. We will solve these equations, and these equations are differential equation. So here in time domain, we can solve first order differential equation. We'll get two types of differential equation. One is homogeneous equation, another one is non-homogeneous equation. See the pattern? Homogeneous equations di by dt plus p I of t is equal to 0 here, where p is the constant. Solution of this homogeneous equation means we want to find I of t. So solution is I of t is equal to k e raised to minus pt, where k is the value we can obtain by putting t is equal to 0 in this equation. Now non-homogeneous di by dt plus pi of t is equal to q. Here it is 0, here some constant q. Solution is q by p plus k e raised to minus pt, where k you can obtain by putting t is equal to 0 in this equation. So this k is nothing but initial conditions. So in the third step, whenever you will apply KVL or KCL, you will get any one of this homogeneous or non-homogeneous equation. Then you can easily solve this because we have a solution for homogeneous and non-homogeneous equations. Let's start the example. In the following network, the switch is changed from position A to B at t is equal to 0. Steady state conditions have been established at position A. Determine I of t at t greater than 0. In case of initial conditions, we are finding I of t di by dt d square I by dt at t is equal to 0 plus. But here in this type of example, we are finding I of t for t greater than 0, any instant of time which is greater than 0. Now here it is given that switch changes from position A to B, and before switching steady state conditions has reached. Means at t is equal to 0 minus, our first step, draw the equivalent network at t is equal to 0 minus. At t is equal to 0 minus, your circuit is like this. Your switch is at position A. So at t is equal to 0 minus, it is given that network attains steady state condition. Means what? Some constant current flows through the inductor. It has reached to the steady state means some constant current flows through the inductor. That is the one steady state has achieved. That means we want to find that constant current. So at t is equal to 0 minus, inductor acts as a short circuit because we want to find that constant current. So here constant current is this I of 0 minus is 10 divided by 1, that is 10 ampere. So this is nothing but current flows to the inductor. So this is, we can call it as a IL of 0 minus is equal to 10. And this loop current is also I of 0 minus is 10 ampere. Now next step is draw the equivalent circuit at t is equal to 0 plus. At t is equal to 0, switching action happens. But remember, for inductor, whatever the state of inductor at t is equal to 0 minus remains same at t is equal to 0 plus. So IL0 minus and IL0 plus remains same. So some constant current which flows at t is equal to 0 minus, that is 10 ampere, will also flow in the inductor at t is equal to 0 plus. And to show that it is a constant current, will represent it as a current source. It indicates it is a constant current, that is the IL0 plus is 10 ampere. Now the third step is draw the equivalent network at t greater than 0. This is our original network. Then equivalent network at t is equal to 0 plus is this one. This is initial current flows through the inductor. Now for t greater than 0, whenever we are representing inductor, we need to check whether there is an initial current exists or not. If it is, what we will do? Inductor in parallel with that initial current IL0 plus. So this is 1H and IL0 plus is 10 ampere. Now we can apply KVL here to find the I of t. We'll take that circuit again, equivalent network for t greater than 0, and we have to apply KVL. Apply KVL. So minus 1 I of t minus 1 I of t minus L di by dt is equal to 0. So within this loop, three elements are there, these two resistor and this inductor. The voltage across inductor is L di by dt. Now in previous type of examples where we are finding initial conditions, what we are doing at this step, there is a change. At this step, in initial conditions, we are putting t is equal to 0 plus, and we are finding di by dt, d square I by dt square at t is equal to 0 plus. But here we want to find I of t for t greater than 0. So in that case, we'll try to solve this differential equation. For that, you need to check whether this is homogeneous or non-homogeneous differential equation. Let's combine this I of t term. We'll get minus twice I of t minus L is 1 di by dt. So multiply both the side by minus, we'll get di by dt plus 2 I of t is equal to 0. Now this is our differential equation. So at this point, we have to check whether it is homogeneous differential equation or non-homogeneous differential equation. It is equal to 0. So this is first order homogeneous equation. We know solution for homogeneous equation di by dt I of t plus p I of t is equal to 0. Solution of this is p is equal to 2 here. If we compare this standard homogeneous equation with our equation, p is equal to 2, and solution I of t is equal to k e raised to minus pt, where p is equal to 2 here. And to find the k, what you have to do? You have to put t is equal to 0 in this equation. So to find the k, t is equal to 0, I of 0 is equal to k e raised to minus 2 into 0. So e raised to 0 is 1. So k is equal to I of 0. I of 0 is initial condition, that is 10 ampere. So k is equal to 10. Put this value and you will get the solution of your example. I of t is equal to 10 e raised to minus twice t a. Ampere is the unit for the current. So 10 e raised to minus 80 is our solution of this network. So here remember in the previous videos we solved the example based on find initial condition. Steps are same. Here also steps are same. Only at this point whenever we are getting integer differential equation, in initial conditions we are putting t is equal to 0, but here we are not putting t is equal to 0. We are solving this differential equation and we are comparing whether it is homogeneous or non-homogeneous. Depending upon that, we are finding its solution and we are getting this solution for I of t. I of t, current flows through the network for t greater than 0. Like this, you can easily solve this type of examples. Practice it. Thank you.